Hello and welcome to the homework video for page 60. These were the assigned numbers. Yeah, let's begin going through it. This is all about spanning trees. For each graph below, explain why it is or is not a tree. Graph A contains a circuit right here. So it cannot be a tree because that's definition of tree. It doesn't allow circuits. So it contains circuit. B, this is a tree because it's connected, it has no circuits, that's all you need. So it is a tree. Connected, oh sorry, maybe no, it contains a circuit. Yes, connected, and it has no circuit. Good. Part C, right here. It only goes between these two vertices, but there are multiple circuits here between these two vertices. Because of that circuit, it is not a tree. Contains circuit. Good. Part D, way up here. D is not connected, so it could be looked at as two trees. We could actually call that a forest, but it is not a tree. So part D, not connected. Part E, at first glance it looks like there are circuits all over the place here, but if you picture taking this vertex and swinging it out, you would see this would go up and around out there, and this would go in, and that would go through. There are no circuits here actually. Now if there were a vertex added there, then this would have a circuit and would not be a tree. But this is a tree, it's just drawn in a way that's misleading. So, oh, and I didn't say that's not, I didn't say that's not. This one, yes, and the same reason as B would apply. F, right here, I'd be looking for circuits and connectedness. That is a tree, and it would have the same reason as B. 51. For each of the diagrams below, explain why the wiggly edges are not A, a spanning tree, and B, a Hamilton circuit. For A, this is not a spanning tree because it doesn't touch every vertex. So, why it's not a spanning tree, doesn't touch all vertices. Good. Part B, why is this not a spanning tree? Oh, again, it doesn't touch every vertex. So B would be the same as A. It doesn't touch that vertex right there. C, this does touch all vertices, but right here it contains a circuit. So not a tree, can't be a spanning tree. Contains a circuit. And then part D, this piece is not connected to the rest of this. So since it's not connected, it cannot be a tree, therefore not a spanning tree. Not connected. Part B. We want to tell why it's not a Hamilton circuit. This doesn't touch all the vertices, so that would be the same reason as there. It doesn't touch all the vertices. B. It doesn't touch all vertices again, so I could say that. Also, it doesn't make a circuit, so I could also say that. I'll say it doesn't touch all vertices, and it's not a circuit. And it can't be a Hamilton circuit if it's not a circuit, obviously. C, this contains a circuit, but it's not like a circuit itself that touches all vertices. So, first of all, I could say it has this tail piece here. I don't know. It touches all vertices, but it's not a circuit that goes around all vertices returning home. So I'll just say it has I'll call it a branch. Because on a tree, we would call this piece here a branch, even though this isn't a tree, but it's not a circuit. D is also not connected, so that's another reason for it not to be a Hamilton circuit. 52. Find all the spanning trees in the graphs below. 52, part A. one spanning tree would go here and take those 2 branches. Another one would go here, go down there and up. And another one would go here and wiggle through there. So part A, I've got D, E. There's 1. There's 2, and there's 3. Those are all 3 spanning trees for this graph. Part B, I could go here and go branching everything from C. I could go here and go all the way around the box. I could go here and go all the way around the box that way. I go here, branch there, and go around this piece. I go here, branch that way, and go straight there. Let's draw some of them. So it makes like a little square, which is, I could do this. I could do this. I could do this. And I could do this. I could do this. I think that might be all of them. I feel like there should be one more, but I can't picture how it would go. That may be all of them. Either way, the purpose of this problem was for you to get used to looking for spanning trees in something, and this is the idea that you should have stuff like that. And then part C, okay, I've got this circuit thing. Oh, whoops, that's not what it's like at all. So I could go around like that. Really, it's going to be a series of which side do you leave out in this case. So I could leave out that piece. 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 I think that's all of them that I see for this graph down here. 53 asks us, use Kruskall's algorithm to find a minimum cost spanning tree for A, B, C, and D. In each case, what is the associated cost with the tree? So, part A. If I can get it on the camera. Okay, part A. Kruskall's algorithm says I'm going to start with the cheapest edge, which is this. Then I'm going to add in the next cheapest edge, which is 2. The next cheapest edge is 3. The next one is 4. The next cheapest edge is 5. The next cheapest edge is 6, but I don't need it. I've already touched both of its vertices. It would create a circuit, so I want to leave 6 out. The next cheapest edge is 7. Again, I want to leave it out. It would create a circuit here. I don't need it. I've touched both its vertices. I'm good. The next cheapest edge is 8, which is there. Now I have a spanning tree. The weight of that spanning tree is going to be 8 plus 1 plus 2 plus 5 plus 4 plus 3. So that's 10, 5, 9, 23. 23 is going to be our weight for A. Part B looks like, maybe I can go side by side. Part B looks like that. Okay. I'm going to start with the cheapest edge, which is 1, and I have tying edges here, which are also 1 and 1. Then I'm going to add in 2 and 2. Then I'm going to add in 3 and 3. Then I would add in 4 right here, but it would make a circuit. I don't need it. I've already touched both of the vertices around it. I'm okay with 4. I can add in 4 down here. think I'm good, so I'm going to go 5 there. Believe that's the only 5. 6, I'm going to leave 6 out here. It would create a circuit. I've already touched both those vertices. I don't need that 6. I can do this 6 to connect those pieces, and I can do this 6 to connect the bottom to the top. I believe that's a spanning tree. It touches every vertex, and it has no circuits. The associated cost then is going to be 2, 3, 1, 6, 2, 6, 5, 4, 3, 1, and 1. So that's 6, 7, 8, 9, 10, 11, 14, 25, 29, 33, 34. 34 would be our associated cost with that spanning tree.